All right, great. So we'll begin. Happy Friday, everybody. I hope you guys are doing okay, more or less. Okay. Well, let's see. Week 7 Friday. Only 3 weeks left after today, huh? 8, 9, 10. Finals, graduation. It's so crazy. It's so crazy. I'm gonna miss you guys. All right. Okay, so we're talking Markov chain Monte Carlo, and we're going to do the Metropolis algorithm for trying to decipher some text. Okay, and all right. So this is what we've got. We got MCMC for deciphering text. And effectively, what we are doing is we're going to, kind of almost Bayesian, but, well, it's barely Bayesian, in that, we're trying to figure out the probability of some letter mapping, okay? A mapping being, the letter A corresponds to the letter E, and C corresponds to the letter K or something, because we've ciphered this text, right? And we want to find the probability of the mapping given our text, okay? And we know that, from Bayes' rule, that this is going to be proportional to our text given a mapping times the probability of our mapping, okay? And then, divided by the probability of the text. But as far as our mapping goes, this will be uniform, okay? Pretty much all 26 factorial potential mappings are equally likely. Right? And so if that's the case, then the probability of a mapping given the text is going to just be proportional to the probability of the text given the mapping, right? So that makes things even easier for us. And on Wednesday, we talked about one model for evaluating the probability of a text given our mapping. So we have a simple kind of two-part model. All right? And so when we say, what is the probability of our text given a mapping? Okay. This probability is going to be the product of, we have a bunch of, we're going to look at the probability of each word in the text according to a lexicon, right? So according to a lexicon. So we're going to look at the probability of each word in the text according to the lexicon given a particular mapping, okay? So that's going to be one set multiplied by the product of the probability of each, basically two-letter combination that appears in the text. Given a particular mapping. So the way we're going to evaluate this is we've got our ciphered, mixed up text, and then we apply a, translation mapping, okay? And this translation mapping will probably map to garbage, but maybe we'll get a translation mapping that maps to something good. And the way we're going to evaluate it is we're going to look at, did real words appear? If that does, then that's good. Or do common two-letter two-letter combinations appear, right? So do we see combinations like TH and IN and OS and whatever, okay? And this is just a very, very simple model for evaluating the probability of a text, right? Because, there are much more complicated and better models for evaluating text probabilities. Here we're looking at just one word at a time, and we're saying like the word "the" is common, and that appears in our text. That's a good sign, right? The word "house" is a common word, so that's a good sign. Okay. Whereas probably your phone has text prediction on the keyboard. Okay, and that's based on something much more complicated. Okay, it's based on they have n-gram things. N-gram meaning like n words in a sequence. So for example, if you see the word going, what's the likely word that's going to follow going? To, right? Going to the store, or I'm going to buy a car, or whatever. So in other more complicated text models, the phrase "going to" is going to have a much higher score than going tree or something like that. Okay, and something and you'll have probabilities associated with kind of these n-gram or multiple word sequences, and that's how your text predict works. You can keep using the middle prediction button, and it'll produce something that sounds almost like English but not quite a coherent thought. Okay, because each kind of like 2 or 3 word combination like sounds reasonable, but then when you string 50 of them together, it doesn't make any sense, right? And so this is very, very simple. We're not going to take into account going to or anything like that. It's just going to say going. Oh, that's a real word. Great. To, that's a real word. Great. Not saying like going to. That sounds very, very good, or something like that. Okay. So this is just a very simple model, and of course, all of these things you can improve by making your models more complicated and whatnot. But as far as a deciphering thing, I think this is adequate, and so this is where we're starting. Okay. And then, of course, because we're multiplying a whole bunch of small probabilities together, for the computer, this produces a problem. And so instead of dealing with the product of a bunch of small numbers, we're going to turn them into logs, and we will add the logs together. Okay, so logs are like totally great. That's how we got to the moon, right? We used slide rules, which are based on logs, and did our multiplication that way. Okay. When I say we, I'm talking NASA scientists, not us. Okay, and then all right, and so the Metropolis algorithm. If we think about what the Metropolis algorithm or the Metropolis Hastings algorithm, what is its purpose? Its purpose is to draw a sample from our target distribution, right? And so it seems weird that like we would use a sampling method to try to get our code deciphering, right? So Metropolis algorithm, tries to get a sample from a target distribution. Okay. So if we think about what is our target distribution, it's the probabilities of over all 26 factorial possible mappings. And if we think about that, almost all of those mappings are total garbage, right? Almost all of them will have probabilities that should be very close to 0. Not exactly 0, but should be very close to 0. That, some garbage gibberish was the intended code that the prisoner was trying to send to his friend. I mean, it's possible that they're just playing a game of sending gibberish to each other, but that's unlikely, right? So But so the Metropolis algorithm, remember the algorithm is trying to get something from the target distribution. And if we think about the target distribution, pretty much all the mappings are garbage, but some of the mappings will be reasonable. Some of the mappings will have decent probabilities. And the beauty of the Metropolis algorithm is that you don't have to evaluate all of them. You can start off in a terrible location, and because of its acceptance probability, it's going to favor mappings that are better, incrementally better, and eventually get you to a location of high probability, okay? And so in the beginning, one garbage mapping, and we can propose another garbage mapping, but some of these garbage mappings will be slightly better than the other garbage mapping, right? Like the garbage mapping that says, we're seeing words like QQXJ, that's really bad, whereas a garbage mapping that replaces the Q with E, and so now we see EEXJ, that seems a little bit better because at least EE is like a common set of characters that we might see in words, right? We would see there's lots of words that have EE in it, whereas there's hardly any words out there that have QQ in it, okay? So if we propose, let's swap the Q and the E, that would probably be accepted because that's going to be a better, it's still a garbage mapping, but it's a better one, okay? All right, so Metropolis algorithm tries to get a sample from our target distribution. So our target distribution, it is, the distribution over all 26 factorial possible mappings, okay? And, nearly all are garbage mappings, okay? Okay. But some garbage mappings are better than others. Okay, so XQQJ versus XEEJ, okay? Both are nonsense words. Both are nonsense, but XEEJ looks less bad, all right? And so, the Metropolis algorithm will favor proposals that are better than the current, okay? But it's also not strictly every step has to improve, right? It's not that every step has to improve because you might have some other proposal that isn't as good, but the Metropolis will accept, ones that are worse just at a lower probability, okay? Yeah, question?
One question that I just generally about the Metropolis algorithm, is there some type of requirement where like the possible values, like there should be an area where it goes to a higher probability, it's all just in a bunch of discrete areas where there's
So if you think about the space is not this, it's weird, right? And so yeah, if there, so not in our example,
right,
but yeah, if you have a situation where the thing is like this, okay, and depending on your proposal distribution, so if your proposal distribution has a tiny sigma, it's going to get trapped in here because every time it proposes something out here, it's going to get rejected, right? If you have a big enough sigma where even though you're over here, you can propose something over here, then you'll be able to make that jump, okay? But yeah, this is a known problem. This is kind of like the bottleneck problem. It's similar to, because the Metropolis algorithm at its heart is a random walk.
Right.
And so, and if you, like, Brownian motion is also a random walk. And so there's examples where, if you put some kind of particle, you can imagine like two spheres of gas connected by a thin tube, okay? And you can put some kind of gas over here. It takes a lot longer for that gas to permeate over to the other side because it has to traverse the very thin tube that's connecting the two, okay? So yes, yeah, and especially if this is a truly zero probability area, then you might get stuck just on one side of the thing, okay? But, and it's also Metropolis because we have a symmetric proposal. So, I mean, we could do Metropolis Hastings with an asymmetric proposal. That's not a problem. We have the acceptance ratio for that. But in this case, it's a symmetric proposal because all we're doing is, each proposal is, here's our current mapping, our proposal, we're going to switch two letters. Should I switch the Q with the E, okay? And which means, if I make that switch, there's an equal probability of proposing the opposite switch, okay? Because all you do is just randomly selecting two letters at a time. So it's 26 times 25, 1 over 26 times 25, so 1 over 650. That is, there's 650 possible switches that you could propose, and all of those switches are equally likely. So we have symmetric proposal. We swap two letters in our map as a proposal. There's an equal probability of swapping them back. Okay, so I have this coded up, and so let's take a look. I'll walk us through the code, and I hope it makes sense, and then we'll let it run. It worked in the first class. I hope it works in this class. Okay. So anyway, credit where credit's due. I'm basically using some code from two different sources. One is from this guy, Andrew Landgraf, and then the other is from a book called Machine Learning for Hackers by Drew Conway and John Miles White. And basically I'm combining the two. So Andrew Landgraf is using just the two-letter transition probabilities only. John Miles White is using the words, and I said, well, you know what, let's merge these two together. Okay, so this initial part of the code is setting up our two-letter transition probability matrix. So we're going to have a 27 by 27 matrix, A through Z and space, and across the top A through Z followed by space. And each intersection is how likely is this probability. So the row T and the column H will say T followed by H should have a high probability, okay? Whereas the row X followed by J, that should have a very low probability, okay? So that's what we're doing. So we're, and the way we're gonna set up this transition matrix is we're gonna read in the text of War and Peace, War and Peace being the famous Russian novel that's super long. It's been translated into English, and we're gonna just read in, all of those lines of text. I'll just start it off. There's like 65,000 lines of text, and maybe it's a little bit too long to, oops, let me set my working directory. Okay, so, here we go, and if I do reference like the first 10 lines, this is the Project Gutenberg ebook of War and Peace by Leo Tolstoy, and we can, get lines 40 through 45. Wait, apparently, all right, let's do 400 or 4,000 to 4,005. Okay. Oh, there's a bunch of gibberish characters here. Okay. See how these nestlings are growing up And she pointed to the girls. Okay, you must look for husbands for them, whether you like it or not. Okay, so anyway, we're going to read in this text and use this for, there's a lot of, I didn't realize there's a bunch of like strange characters here. I think these are like quote marks that just got messed up, but okay, well anyway, our thing is going to ignore all of these things because they're not letters. We're only considering the letters. Okay, so our transition matrix is going to be 0 through 27, and if we take a look at our transition matrix, we start off with a whole bunch of zeros. Okay, and what we're going to do is we're going to go through each line here, and we'll say like, okay, always, and we're going to say it's going to start off with space A. And then we will put in a probability from going from space to A, and then we will go to AL, and we'll add 1 to AL, and then always LW, and we will add a tally at LW, and so on and so forth. And we're going to do that for every single line, and that's what this code does. It says, for each line, look at the number of characters in that line, and then your current letter is going to be, so it starts off with last letter being space, and it says, your current letter is going to be the letter in this position, and then what you're going to do is, in the transition matrix, find the row with the last letter, and find the column with the current letter, and take that and just add 1 to whatever value you have there. And then assign the current letter to the last letter, and then loop around, find the next letter, and keep adding 1 to each cell. Okay, and so we can run this, and as it's running, it's going line 1000, line 2000, line 3000, line 4000. It's running through all of these things, and I'm going to just stop it here at after 7,000 lines. We could sit and wait for all 65,000 lines, but just in the interest of time, we won't do that. Oh, shoot. I zeroed it out. Okay, so let's just do a few thousand lines, and you'll get the idea of what this transition matrix looks like. Okay, so this is after 5,000 lines. My transition matrix, shoot, did I do this wrong? Okay, I think. All right, so there we go. Okay, so after about 7,000 lines, okay, we see we haven't seen any words where A followed by A. I mean, that happens in English in like the words aardvark, but apparently not yet in our 7,000 lines of text, okay? We see a lot of words where E is followed by A, and we can kind of go down and we can see, T followed by H. That happened a lot, 6,807 times, okay? Whereas T followed by D didn't happen very much. T followed by C happened by 82 times. T followed by B happened 5 times, okay? And then there's a lot of combinations that did not happen, like Q followed by any letter happened 0, 0, 0, all of those 0 times. Q happened followed by U happened 248 times, but Q followed by any other letter so far has happened 0 times, okay? And we can see, lots of letters or lots of words end with E. This is E followed by space. That happened 11,432 times. D followed by Z happened 1 time. It's something like that's, I don't know. What's a word where D follows, Z follows D? Whatever. Okay. It's there, L followed by Z and stuff. Okay. So anyway, we're gonna just take the sum of this thing and turn them into probabilities, and just by taking each cell and dividing by the sum. However, if I did that, these cells with zeros would have 0 probabilities, which is a problem because if that 2-letter transition appears in our decoding, it's going to say it has a 0 probability, and that's going to zero out the whole thing, because as soon as you multiply by 0, it zeroes it out. So instead of zeroing it out, we're going to just add 1 to every single cell, so none of the cells have 0, and then I'm going to divide by the sum. I probably should do divided by the sum of the thing plus 27 times 27, but that's okay. My transition probability matrix will have a sum that's just ever so slightly bigger than 1. Not a huge deal, okay? All right, anyway, I've done it for all 65,000 lines of text, and I'll go ahead and load those in. And that represents our two-letter transition matrix, and we can create a plot of this. And so this is what it looks like, and we can see indeed T followed by H. That's one of the most common transitions. H followed by E is also very common. E followed by R is a very common one. So the dark ones represent common things, and you can kind of spot which rows are vowels because they happen. These rows appear much darker. The A, E, I, and O. And then you can also see the columns that are darker, A, E, I, and O. Okay, other common letters, R and S and T, and R followed by E, S followed by E, T followed by E. These are all very common. Whereas other things less common. Okay, so that's what we have. A lot of words begin with T, a lot of words begin with H and A, and a lot of words end with E, a lot of words end with M and N and S and T and stuff like that. Okay, so that's our two-letter transition matrix. Okay, this is a function to go from text to kind of decoded text. Okay, so let's. I'm going to set up a map, and this will be, I'm going to just sample the letters. So here's my map. So this says A goes to the letter U, B goes to the letter H, C goes to the letter A, okay? And then so I could take this function decode, and we will provide it my map, and I'm going to say code the word hello, okay? And it says when you code that up, you get BGYYP, okay? All right, and then so the D map I would have to take our letters and do order of map, I think. So yeah, A corresponds to U, B corresponds to H, and C corresponds to A. So this would be the D map where C corresponds to A, Z corresponds to B, E corresponds to C, and we can kind of see this work out, right? So E corresponds to C, and then so if I use decode using the D map, and I put in BGYYP, then it puts back hello, right? But most likely, when I decode, if I don't know the thing, it's just going to be another thing of letters, and so I'm going to have BGYYP, okay? And that says, okay, well, when you tried to decode it, you get IUVVC, and we'd say, well, that doesn't look right, okay? And I could say, well, let's try another thing, right? So this would just be like pure random, like, I'm going to pick, this would be like uniform sampling, right? We're just going to propose one random thing and just see, and then we're going to say, is this right? No, that's not right. Is this right? No, that's not right, okay? The Metropolis algorithm will say, like, between this one and this one, like, well, this one looks better than this one, I don't know, and between, Vigizitor or versus Vikulth, like, which one is better? Like, these both look terrible, and I don't know which one the Metropolis algorithm would favor, but obviously this is the best, and But I would say IU looks like a better letter probability thing than any of these other things. All right. So anyway, that function just codes them and decodes them, okay? And then log probability, this is going to apply the, find the log probability based on the two-letter transitions. So what we're doing is we take our mapping and we take our text as it runs through the decoder thing. So here we're proposing like VQLLT, and we say, okay, well, what is this? So it's going to go through here, and it's going to basically look up each letter combination. It's going to say, well, okay, what's the score associated with VQ? And we're going to add that to the log probability. Log probabilities are negative, right? Because all of our probabilities are between 0 and 1, and so the log of any number between 0 and 1 is negative. So we start off with 0, and then we keep adding these negative numbers by looking them up in this table. We're going to be like, okay, VQ, that didn't happen. That's going to have a very negative number. What about QL? That doesn't seem to have ever happened. Okay, LL, oh, that happens sometimes, so we'll add a less negative number, okay? And LT, that also happens, so we'll add a less negative number, and we get some kind of score here. And it's these ifs and these else ifs, these are all for like handling the space. Like once it reaches the end of the letter, you know, T followed by space, those get added in, and so we'll get the log problem. So actually VQLLT, because of the LLT, might actually not be terrible. But anyway, okay. So that's gonna give us the score based on the two-letter transitions, okay? This is the code taken from Machine Learning for Hackers, where we're using the lexical database. And I'm honestly not sure where the lexical database is coming from, and it might not be super accurate. But basically, each word in the lexical database has some kind of score associated with it. So if you do this will have the highest probability, and it says about 5%, a little over 5% of words in English are the word the. You know, the word house, appears about 0.004, okay, versus, maybe the word car happens a little bit less often than house. What about run? Well, apparently more often than car, but less often than house. Okay, I'm not sure. But then, you could ask for strange words like aardvark, okay? Aardwolf, how often does that happen? Okay, that happens on the order of 1 times 10 to the negative 7. And then if you give it some gibberish thing, it's going to say that that's not in there, okay? And so we are going to calculate the log probability of the text. And what the text does is it's going to split it up based on at spaces. And we're going to have a string, a vector of words. And we're going to look up each word in each word in the database, okay? And so the 1 gram probability is basically just one word at a time. And if it's null or if it's not in the database, we're going to return just a small value, like 1 times 10 to the negative 10, okay? Just so we don't want to have zeros in there, because log 0 would be negative infinity, and multiplying by 0 out our probability. So we're just going to put in a small value that says this is an unlikely word, okay? So we will put that in there, and then log probability of the text will do that, okay? Does this all make sense as far as how the system's evaluating? Okay, so now we've got, this is our text that we're going to run. It's going to be from Hamlet. Enter Hamlet. Hamlet says, "To be or not to be, that is the question. Whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or to take arms against a sea of troubles by opposing end." Okay, so thank you. We're going to start off with just some random seed. Okay, well, not a random. This is an arbitrary seed. Okay, and then we just we're going to encode this. And when we look at the code, this is when we map this, right? This is the secret message that you are passing to your friend, right? And so you've written, you know, okay, and you know, your teacher intercepts this, or the prison guard intercepts this and says, "Oh, I can't understand this. What are these people up to?" "Oh, we're just quoting Shakespeare. Don't worry about us." But that's what we have. And so, okay, well, you say, maybe we'll have a random mapping. Okay, so the random mapping says, all right, let's map the letter A to V. Let's map B to F, and the letter C to S, and stuff like that. All right, so let's apply that to our coded text. And what does this look like? Well, okay, so we've mapped B to the letter F, and so if we decode that, you know, we're going to have B, and this is our translation, and it's also gibberish. Bukibu, fradbi, frad, you know, this is no good. And we can say, all right, well, let's just see what score this gets. Apparently I didn't hit enter somewhere. All right, so we'll run this, okay? And so this is the score associated with the two-letter transition, and then this will be the score associated with the word probabilities, okay? And we're going to combine these two. Now, here I have this adjusting weight to kind of just say, like, which one of these is more important. And so I'm actually going to weight the ones based on words less than the ones based on the two-letter probabilities. This is kind of just based on like fiddling around with some stuff, okay? And then we're going to just say, this is my current decoding, and we're going to set, what we're going to do is we're going to keep track of which one produces our best score. Because remember, we're not actually doing any kind of optimization. We're doing the Metropolis algorithm, which naturally will sample areas of higher probability, but inside the Metropolis algorithm, there's nothing that says you must get the best. And so we will just keep track, like, what was the most probable value that we saw, or the probable mapping we saw, okay? And then we'll do this. And so we're going to just start off, and so in each iteration, we propose basically from, we're going to say, take two letters and swap them, okay? And so our proposal mapping will be our current mapping, and we're going to just swap the positions of two letters. So we might say, like, let's propose switching E with the letter Q and see what happens, okay? And then we will apply that decoding to our thing, and we're going to say, like, okay, if we did this swap, what would our decoded text be, okay? And so the decoded text will be almost exactly the same, except if I swapped Q with E, then this would become BEIBU, and this would become EYI and EYX, and we'd say, oh, maybe that's a tiny bit better, okay? And so we'd calculate this out. We find the probability score based on the two-letter transition. We find the probability score based on the words that appear, and then we combine those two. And then because we are dealing in logs, we exponentiate them. And I can't remember why I put a 0.5 here in the code. I'll have to figure this out, but this is something I wrote a little earlier. And so, you know, we take the difference, and this is going to be kind of like, do we accept this proposed value, yes or no? So if a random uniform number is less than kind of the proposed probability, then we will take our proposed mapping and assign it to our mapping. Our current, we update our current decoding, and we'll update our current score, okay? And we just do that. Okay, so let's try running this and see what happens. So again, this is where we start. Our current mapping produces this as output. And so, you know, we start off here, and immediately we can see, you know, we're starting to switch things out. And even though this still looks terrible, like, at least we're now in a position where we have a decent mix of vowels and consonants in the words, okay? And, this is still gibberish and nonsense. It doesn't make sense to us. But you might be able to convince someone that this is like a foreign language or something, right? Because there's a good mix of vowels and consonants, right? Because whereas before, where it was all just like, BQ, whatever, it didn't look good. And now we're getting things that kind of look a little bit, a little closer to English. These are not real words, okay? But here it goes, It's, now we have entes lakwet lak to be, os not to be, and it's figured out not to be and stuff like that. And, we've got nobles in the pinned to ruffles the relinger, but it's starting to get closer, and we've found like fostuin, vortian, entes, haplets. So it doesn't quite know, but it's at this point it's starting to look pretty good. Okay, at this point we would probably, as humans, recognize like, oh, this kind of looks like Hamlet. We got entes, hacklet, hack to be, os not to be. That is the question. Chether, 'tis nobler in the kind to summer the slings and erics of outrageous. Oh, look, here we got it. Enter Hamlet, ham to be or not to be. That is the question, whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or to take arms against a sea of troubles, and by opposing end. And it seems to have found it, and it's still going because it's still trying to sample. But now we're at a location where the probability is very high, and everything it's proposing is probably not as good. But it will still accept these less good proposals because that's the Metropolis algorithm. It's not strictly optimizing. It's just trying to take things that have higher probabilities, and here we are. We've pretty much decoded it. Okay, I'm going to go ahead and hit stop after 190 iterations, and we could see the max decoded thing. Let's take a look, and the one that produced the highest probability of decoding is indeed the solution to our, well, okay, not exactly. It has question with C, Houston, but other than that, it seems pretty much as good as it's going to get here. Okay, and so I think that's cool, right? So this is a situation where, again, if we look back at what the actual distribution looks like, okay, this is a very difficult thing because there's technically the true distribution is divided by the probability of the text. And the probability of the text is what is the probability across all possible mappings, and there's just too many values to evaluate. But because our acceptance ratio is a ratio, that constant drops out or cancels out, and we only have to worry about this without worrying about the actual distribution and having it sum up to 1 or anything like that. Okay. I thought this was pretty cool. I'll post up the code. You guys can take a look at it, and that's it. Have a great weekend, and we'll see you guys on Monday.